Hello students, welcome back. Previously we went through the definition of the group and we had these three important properties: associativity, identity, and inverse. Let's go back to the identity. We assume that the existence of the identity. How many are there? We did not discuss. There may be one, there may be two, there may be 15, or maybe there are infinitely many. Well, if you have infinitely many, then we really have a problem. If you have 2 or 3 or 4 and so on, still those are going to be problems. What we want is there's one and only one identity, or the uniqueness of the identity that we want. The uniqueness. The same goes to the inverse. Given x, we assume the existence of the inverse. But there may be more. There may be y, there may be z, there may be others, maybe infinitely many. Well, if so, we are in trouble. We claim that there is one and only one inverse for given element x. We want to establish those two uniqueness properties, and once that uniqueness is set, then we're going to call it the identity because we proved that there's only one, and we're going to call it the inverse of x because we just proved there's only one. Well, actually we didn't prove yet, but we will shortly. Okay, let's go ahead and prove there's only one identity. How do you prove that? Here's a general technique to prove anything associated to uniqueness. Assume there are two, E1 and E2, and then prove that they're the same. Or assume they are different and then derive some contradiction. We're going to take the first approach. We'll assume E1 and E2, and we're going to prove they're the same. How do you do that? And somehow we have to use this property, of course, because that's what makes the identity. So here we go. Suppose that we have E1 and E2. And then we want to prove E1 and E2 are the same. So E1 and E2 with this property, then they're the same. How do you prove that? Well, okay, let's stop here. Think about how to do that. If you have no idea, then okay, what choice do I have? I have to show you the answer. Here we go. It's that simple. Let's analyze this a little bit. Please note that E2 is an identity. I just highlighted in blue. So we have this property. Something times E2, we get the same thing back. That's what we have here. We have the same E1 back because E2 is identity. Make sense? Now, E1 is identity. So E1 has this property too. Everything will stay the same. So E2 will stay the same. Consequently, what did you get? E1 is equal to E2. And then we use both properties. E2 is identity, so that we get this, highlighted in blue. And E1 is identity, so we get this, highlighted in red. That's the proof. Simple, but it's hard to think of this way, at least at this moment. But doing this one more time, hopefully you can get some idea. Okay, let's do this again. This time, let's prove there's one and only one inverse for given x. So x is fixed. That's arbitrary, but fixed. And there exists a certain y. As before, we're going to use y1 and y2 and establish that they are the same. Okay, so we're going to do kind of like this, y1 oops. Okay, that's what we want. And of course, we have to prove using this, the property of inverse. So how do you prove this? Using this. Good question. We may have to get something like y1 is equal to something, and then eventually that's equal to y2. How do you work this part out? Somehow we have to use this. So E is getting involved here. Any idea? Okay, let me give you just one more hint. So that's equal to y1 times E. So you see, y1 is equal to y1 times E because E is the identity. And then somehow you have to work out and you're going to get y2. Or maybe you see the picture. This is y2 times E. Or it could be E times y2. Why do you think I changed the order? Obviously, I was giving you a hint. Did those help? Okay, here we go. So that's what we want. y1 is equal to y2 somehow. How do you set that up and how do we prove it utilizing this? Okay, y1 is y1 star E, so far so good, but E is x times y2. We already have y1, so it's time to get y2 involved. So E, which I highlighted in blue, is x times y2. Get that? Next, use the associativity and group this y1 and x together and y2 separate. And this falls into this as well. It's E because y1 is also an inverse. So that's E. Make sense? So y1 is y1 times E, and you can rewrite E as x times y2. Okay, we have 3 elements multiplied, so we can use the associativity. So y1 star x times y2, and y1 times x, going back to this, it's E. Consequently, we have E times y2, and that's equal to y2. Feel a little bit okay? Maybe not yet. You may need some similar exercises multiple times to get used to this. But in any case, uniqueness is important. Because we established the uniqueness, you can finally call it the identity. And then we can call it the inverse of x. And furthermore, we can represent y in terms of x. This y can be written as x inverse like this. In case of abelian groups, we sometimes use minus x, but most of the time we're going to use this expression for inverse. So if you have unique inverse, then it can be represented uniquely using x. That's why this expression is valid. Otherwise, it's invalid. If there are two or more, then you can't do that. For example, square root of z for some complex number, this kind of expression is invalid. As you know, square roots, well, for real numbers, we have positive or negative square root. So if you have just square root, then you can assume it's positive square root. But for complex numbers, we don't have positive or negative. So square root expression is invalid, as a matter of fact. It's not unique. Cubing root is inverse, and so on and so forth. We have valid expression only because of the uniqueness. Okay, we just went through something difficult to understand but important. Now, let's go to an application to this. Cancellation laws. Let's try that. The left and right cancellation laws hold. A star B is equal to A star C, then B is equal to C. Basically, we did just this cancellation. Cancel, cancel. Or to the right, cancel, cancel. Make sense? The problem is, can we really do that? Is it true? The answer is of course yes, and we have to prove it. All you have to do is to multiply the inverse to the left-hand side or to the right-hand side. Here we go. Multiply inverse to the left-hand side, and then these two will cancel, and these two will cancel. Consequently, the next line follows. These two go out, these two go out, and those are identities. Consequently, we have B equal to C. That's the proof of the left cancellation rule. And please note that we use A inverse notation because we established the uniqueness before. Otherwise, it would have been far more messy. Can you do the same thing to the right cancellation? Well, the detail is left to the students. Similar to that, but it's left to the students. Let's see. Do we have time for linear equations? Okay, let's go ahead and do that. How do you solve that? Well, by flipping A to the other side. By flipping A to the other side, by multiplying the inverse. Multiplying A inverse, you get A inverse times B. Multiplying A inverse, you get B times A inverse. Multiplication is not commutative in general, therefore you cannot use the same thing twice. To the left, to the right, you have two different proofs and two different versions. Again, everything is following from the uniqueness lemma. How about the next one? Inverse formula. Oh, okay, all right, here's a nice one, but this one I'd like to leave it as an exercise problem for homework. Yeah, I'll leave this as an exercise. The student who went through linear algebra will remember this already, so you can do something similar.